Hello. Hello and welcome to this video. So as we discussed in last video, we were supposed to go through linked list, but I'm taking a small detour only for this video to cover up some important traits. Now, if you look at the traits, there are quite a bit of traits, but we're not going to do all that. I have made a presentation, so you can watch the presentation and we will cover only a very small portion of traits. So let's get started. Also, at the end, I'll show you my website where you can come and ask us questions, and I'll be happily answer those. So let's cover the first. We cover the different topics whose dates we are going to discuss. One is equality, ordering, hashing. Second category is copying and cloning. Third is formatting. Fourth is conversion. Fifth is iteration. Sixth is lifetime concurrency, and seventh is error handling. So inequality, ordering, and hashing, we have partial equality, equality, partial order, and order traits. So partial equality defines equality in the form of is equal to is equal to. Not every type has total equality. For example, F64 NAM. Now, partial order and order are there for less than, greater than, and sorting. Okay. So how we can derive, for example, unsigned 32, you can derive from all these, okay, because U30 supports that. So version can support these traits as well. These are required for hash is required for any key type used in hash map or hash set. Contract is that if A is equal to B, then hash of A is equal to hash B. So once again, U64, if you have U64 or simple primitive type, like U32, U8, and so on, then you can have the hash derivation as well for that kind of structure. Now we implement order manually. So here's the sample code. We have a structure task, priority is U8, name is string. Now if we want to implement odd for task, obviously we need two of those. So one is the self, another is the other, which is of the same type, self, okay, and returns the CMP ordering stuff. So how do we compare? Other dot priority dot comparison, we are comparing the priority with self dot priority. So high priority first. So this will complete the odd implementation for this. And if you want to implement partial odd traits for tasks, then how we can compare this is you return self dot CMP to other, okay, and this might return null. So we wrap that in some enum. So it will be an option, okay. So it may be greater than or less than, but it can return none also. Next, we have copying and cloning. Cloning is explicit, possibly expensive duplication via clone, and copying is implicit bitwise duplication for small stack-only types. A type can only be copy if all its fields are copy. Copy implies clone, never the other way around. This split is what makes Rust smooth semantics predictable. Usually derived manually when a field needs custom duplication logic. So custom duplication logic will be most probably you will need when you are copying or cloning data which do not have clone. Or for example, for pointer types, you will need to do custom duplication logic. So here we have a cache which has a data element of vector of type U8 and hits is U32. Now if you want to implement clone for this, then you put this in impl clone for cache. All the syntax we have discussed earlier when we were discussing traits. So the cache will be data will be self.data.clone and hits you can initialize with 0. So hits resets and clone. Otherwise, you can pass self.hits as well if you show this. Next is formatting. So there are two types of formatting, two main traits. One is debug, another is display. Debug is developer facing output via colon question mark, usually derived. Display is user facing output via braces, always handwritten. So for example, for the version struct, we can implement standard FMT display trait. So how you can display is you can use the write macro and you pass it to F where self.0, self.1 and self.2 can be put inside the double quote string in various different ways, however you desire. And the result is result, FMT result. Next, we have conversion. So there are four main traits: from, into, try, from, try, into. And if you implement one, the other you get for free. For example, from T, you get infallible conversion. Implementing it gives into for free. Try from is fallible conversion, returns result. Where these are used in idiomatic API design favors from over ad hoc new underscore from X constructors. The question mark operator relies on from to convert error types automatically. Then we have asref, cheap non-owning reference conversion from ampersand string to ampersand str, for example. Then we have asmut, which is the mutable counterpart. Deref and deref mut enables the auto deref that makes smart monitors field transparent. These traits are why a single function can accept ampersand str, ampersand string, and more via generates. So we, for example, implement error. So error of from E, let's auto convert error types. So for example, we have an num app error, which can be either an stdio error or it can be a num parseInt error. Okay, so these are named IO and parse. So from stdio error, for app error, we implement this trait and we describe the from trait and we return app error colon IO with the exact error E, which is passed here of type stdio error. So we convert that into app error IO. And similarly, we have read count, it returns result I32 and app error. So here the read to string path, this error will be automatically translated into app error and text.trim.parse. Here parseInt error will be passed to app error. So that's pretty straightforward. Then we have deref type. So it lets the wrapper type transparently expose the API of what it wraps. So we have a meters structure which contains a single field F64 and we implement the ops deref for meters. So target type is F64 and deref on self returns a 64. So we simply return a reference to 0th element. And once we have implemented the deref trait, we can call m.sqrt, which actually operates on F64, but here m is meters and we can call sqrt or directly on this, because this deref will automatically trigger the API of F64 to M. Then we have iteration. As you know, we need only one method and dozens of adapters will come free for it. It is lazy by design. No work happens until something consumes it. So for example, for iterators for countdown, where countdown could be a structure, type item is U32, next is will return option 32, and you can have custom logic to return this option 32. Then we have lifetime and concurrency traits. One of those we have already seen, drop. We have already seen drop. We have discussed it in quite a bit of depth. So I would suggest you to go and watch the video on drop trait. And then we have send and sync. These will be used when we do multi-thread programming, particularly related to mutexes or MPSC channels. So send trait indicates that a type is safe to move from one to another thread, and sync means a type is safe to reference from multiple threads. These are auto-derived by the compiler, where every field qualifies, no annotation needed in normal code. This pair is what lets the compiler catch data races before the program runs. So drop we have already done, so we won't cover it. Then we have error handling. So error and from str are two traits we will cover. We have standard error. That is the type we have. The common interface for error type enables question mark across error kinds. From str powers 42.parse I32 and similar string to type conversion, and default gives a sensible T default without a manual constructor. So for example, we want to implement a parse error for a structure which has one member line of type 32. Then you do implement display for this, okay, display trait, and you impl std error for parse error, and that should work usually very well. So why we use traits and why not inheritance in Rust? So trait gives us composability without a class hierarchy. A type can implement any combination of traits independently. Generic code is written once against a trait bound. For example, the function could be largest, where the type satisfies the order, full order, and items will be a vector of a slice of elements and returns reference to one element. So you see that if the if the type specify the full ordering, then we can compare elements again in the slice contained, which is contained here. And I can figure out the largest possible element by using the comparison operators. And then you can return the reference of that particular element. You don't need to copy and send that element. So this is the mechanism that makes the standard library feel small yet expressive. And with this, we come to the end of our discussion on important traits. And in the next video, we will start with linked list. So if you have questions, let me show you where you can come and ask the questions. So you come to my website, kunjika.rust.org, make a login here, and you can ask me questions related to Rust. Use the tag of Rust to ask questions to me. So this is because large programming based questions, YouTube comments does not work very well. So I developed this for you, and syntax highlighting and all is built in. So for example, you can do markdown help and you will see the usage of markdown editor. So make use of this question answer website to ask questions to me. And with this, I will end this video here and we will meet in the next one discussing linked list. So thanks a lot for watching the video and I'll see you in the next one. Till then, have a great day. Stay curious, keep learning, and most importantly, enjoy.